All right, hello everybody. So I wanted to explain to you a concept that I've seen many times in vectors, but that for some reason it just didn't quite click in my head for why it makes sense. And it was one of those things where sometimes authors would use it as if it was some obvious thing, and I just wasn't seeing the intuition behind it. So um, I want to explain what a projection is, and it was something I could follow a formula on, but I didn't see exactly why it worked, and so I want you to really try to see the intuition behind it. So here's the idea of a projection, and what I'll do first is sort of a simplified projection. So I'm just going to imagine we have a 2D situation. We've got a vector called v, and there's two different projections that I might consider. I might consider kind of the shadow of v here. So I'm going to call that the projection of v onto the x-axis. And I could also consider here in blue the projection of v onto the y-axis. I've seen different notations for how you write the projection. I'm just writing it this way. So it's a projection of v is the vector, and then the little subscript that I'm writing below is what other thing I am projecting it on. Because you can think of the x-axis as just a multiple of the I vector, and you can think of the y-axis as just a multiple of the j vector. And so this is just an idea that any vector can be kind of projected onto another vector, and the way we do it in this simplified example is just your basic trigonometry. You have an angle theta right here. And so the projection is just going to be here. If I look at this, I could create a right triangle. And this is the adjacent side. And so if I write down what cosine of theta is, cosine of theta is the adjacent over hypotenuse. So the cosine of theta is the magnitude of the projection. And I have to do the magnitude to make it into a length instead of making it a vector, divided by the magnitude of v. So that's cosine of theta. And similarly, if I wanted to do sine of theta, that would give me the other projection. So that would be the magnitude of the opposite side, so the projection of v onto the y-axis divided by the magnitude of v right there. Okay, so that's kind of the basic intuition, is that, okay, sine and cosine are how we break a vector apart into its two components. So now let's look at a more generalized example. So I'm not going to tell you what dimension I'm in anymore. We're just looking at two different vectors. We're just looking at vector v and vector w, and they have some angle theta in between them. And what I want to do is I want to look at what is the projection. I'm going to make vector v a little shorter just to make my picture nice. What is the projection of vector v on to vector w? And the way I can do that is I want to just create a right triangle. So this is a right angle here. Create a right triangle, and this is going to be the projection of v onto w. Okay? And so we can follow basically the same logic that I just talked about in our normal xy plane here. Cosine of theta is going to be the adjacent side, so that's the magnitude of the projection, divided by the hypotenuse, and the hypotenuse is just the magnitude of v. Okay, but we can do a little bit better than that, because cosine of theta is defined in terms of the dot product. So if you remember from dot product here, we have that for any two vectors, v dot w is magnitude v, magnitude w, cosine theta. So that means that I can bring these guys on the denominator and substitute that for cosine theta. So what I have is v dot w over magnitude v, magnitude w is equal to the magnitude of the projection divided by the magnitude of v. And so what's really nice is that the magnitude of v can cancel out by multiplying, and you're left over with this wonderful formula here that v dot w, which is pretty simple to calculate, divided by the magnitude of w tells you the magnitude of the projection. Okay, so that's a really nice formula to use. I want to show you an example of how you might use that. So let's erase this junk over here on the left side. And let's look at an example where we have two different lines and we want to find the shortest point between those two lines. Okay? This is really hard to do unless you consider a projection. Okay, so I'll show you an example. Let's say we have one line. Let's just give it, I'm just going to make up a random equation. So I don't know how this is going to work. We're just throwing down random numbers here. So here's one line. And then here is another line. And I'm going to make sure they're not parallel. And I'm going to make sure that I don't use the same point on them. Let's just make it over -1. So those aren't parallel because the direction vectors aren't multiples of each other. And I want to find the shortest distance between those two lines. So here's how you can do it. The shortest distance between two objects is always going to be perpendicular from one to the other. So that makes sense because if you don't go perpendicular, you have moved off of the shortest distance. Going perpendicular minimizes the distance between two objects. And I'm going to find the perpendicular by doing the cross product of the two direction vectors. So the direction vector from my first line, I'll just call it D1, is given just by looking at the denominators, 3, -2, and 5. The direction vector for my second line, D2, is 5, 3, -1. And if I do the cross product of them, I'll get a normal vector that's normal to both of the things. So the normal vector is going to be the determinant of this big old matrix, I, J, K, 3, -2, 5, 5, 3, -1. So that's going to give me I times 9 plus 10 minus J times -3 minus 25, and then plus K times 9 plus 10 again. Oh, okay, I did my I component wrong. My I component should be -2 times -1, so it should be 2 minus 15. Okay. It's dangerous to do determinants in the morning. Okay, so anyway, our normal vector comes out to be, let's see, 2 minus 15. -3 minus 25 is -28, but I've got a double negative, so I have positive 28. And then K is 9 plus 10 is 19. And you should double check that really equals 0 when you dot product that with D1 and when you dot product it with D2. And let's see, that would be 39 and 56 and 85. That looks good. And then 65. Yep, that looks good. Okay. So then what I really want to do now is I want any vector that connects my two lines, and I want to project that vector onto the normal. Okay? So I just need 2 points that are on one point that's on line 1 and one point that's on line 2, and I can project that vector onto the normal vector, and I'll have the shortest distance between the two lines. So that's the beauty of this idea. So luckily, I know that on line 1, we have the point -2, 1, and -5. Those are the coordinates that I get from looking at the numerators. And on line 2, I have the point 1, -1, +1. And so I know that there is a vector between the two lines that goes, the x values went up by 3. So this is just, I'm going to call it vector v because it just connects my two lines. So from -2 up to 1, then from 1 to -1 is a -2. And from -5 to +1 is going up 6. So I'm going from the black line to the red line, and I think I did those subtractions correctly. So the last thing I need to do is do my projection. So I'll use my formula that we got over here that I want to project onto the normal line. So the normal line is going to be my W. I want to project V onto N. So the projection, and the formula tells me the magnitude of it. So the projection of vector V onto vector N is going to be N dot V over magnitude of N, right? And so that ends up being, let's see, so the top is -13 times 3, so -39, 28 times -2. 28 times -2 is 56, right? -56. And 19 times 6 is, what is that? 120, 114 over magnitude of N. And that becomes 13 squared plus 28 squared plus 19 squared. I should mention also that there should be absolute value bars around it because this is a strictly positive distance. So let's just see what happens. I'll show you how I typed it all in. -13 minus 56 plus 114 over square root 13 squared plus 28 squared plus 19 squared. So typing all that in, 0.52. So those lines are pretty close together. So 0.52. So I'll just say they're approximately 0.5 units apart. Imagine how hard it would have been to try to actually find the points of intersection there. You would have had to find out which point on line 1 uses the normal vector to get to line 2. That involves a couple different parameters. It's super nasty with the algebra. So using the projection gets you there a lot quicker. So thanks for watching. Please comment. Let me know. This was a really big conceptual aha moment to me of using this projection formula. So I hope it helps you too.